Good day and welcome back. Today we're going to talk about the alternating current through an inductor or a capacitor. We will combine two topics. We were going to derive the expression of the current and explain the phase difference between the current and voltage for a pure inductor or a pure capacitor. And then we're going to define their reactance and derive the formula of the power in an AC circuit. First, we derive the current in an AC circuit with a pure inductor. We have learned about the induced EMF in the inductor when there is change in current flow. In chapter 16, we have learned that the back EMF is equal to the negative of the EMF source, where the induced EMF is given as negative L multiplied di dt. We are given with the voltage equal to V0 sine omega t, and then we can perform the integration of the voltage with respect to time. In the end, we can obtain the current is equal to negative V0 over omega L multiplied cos omega t. So we can replace V0 over omega L as the peak current, I0, and we can obtain I is equal to negative I0 cos omega t. So before we move on, let us derive also the current in an AC circuit with a pure capacitor. In chapter 13, we have learned that current is the rate of flow of charge, and the charge in the capacitor Q is equal to CV. Differentiate the formula of the voltage, and you will get current is equal to omega CV0 cos omega t. And again, we can replace omega CV0 as the peak current I0. So we have I is equal to I0 cos omega t. Before we talk about the phase difference, let us look at these two formulas to derive their reactance. Reactance is something like the resistance, which defined as the oppositions of a material or a resistor to the DC current flow. It is also the ratio of V to I, which is the formula that we use to calculate the value of the resistance. As for the reactance, it is the opposition of an inductor or capacitor to the AC current flow, and they are also the ratio of the voltage to the current. So from the formula derived, we can obtain the ratio of V0 to I0 in inductor, which is equal to omega L, and the symbol of the reactance is given as XL. As for the capacitor, the ratio of the V0 to I0 is equal to 1 over omega C, and the symbol of the reactance of a capacitor is given as XC. One thing to take note that the reactance is the oppositions to the AC current flow. We have learned how the inductor or the capacitor behave in a DC circuit. The phenomenon during the steady-state operation also can be explained through the formula of the reactance. For DC current, their frequency would be 0, and when you put in the value of 0 into the formula of the reactance of the inductor is equal to 0 ohm, which indicates that the inductor is short circuit when the current is in steady-state operation. As for the capacitor, when you put in the value of the frequency equal to 0, the reactance of the capacitor is equal to infinity, which means that it is an open circuit when it is a DC current flow. Now we're going to look at the phase difference between the voltage and the current flowing in an AC circuit with a pure inductor or a pure capacitor. So the graph response of the voltage and the current is as shown. To analyze the phase difference between the voltage and current, we can take the maximum point as our reference point to do the comparison. So the voltage has achieved its maximum value at the angle of 90 degrees, while the current is at 180 degrees. This means that the voltage in a pure inductor circuit is leading, and the I also can be expressed as I0 sine omega t minus 90 degrees, or it can be I0 sine omega t minus pi over 2. Next, for the AC circuit with pure capacitor, the graph response of the voltage and the current is as shown, comparing both of their maximum value, where the current achieved maximum value at 0 degree, while voltage is at 90 degree. Here we can conclude that current is leading the voltage by 90 degree, and it can be expressed as I0 sine omega t plus pi over 2. Next, we're going to study the power dissipation, where P is equal to VI, and we just do the product of V and I, and we can obtain the expression of the power. So we can see that the waveform of the power in either the inductor or the capacitor is almost similar. From both of the waveform, we can see that the frequency of the power is twice as the frequency of the voltage and the current. And they are also changing their value between positive and negative. Unlike the resistor that we have discussed, the power dissipation is always positive all the time. So when the power is in positive region, the energy is supplied to the inductor, or we also have learned that the capacitor is charging. And when the power is negative, it is the reverse way that the inductor supply energy back to the circuit, or the capacitor is discharging. So we have learned that inductor and a capacitor is a component that able to store charge, and they will dissipate their charge based on the different scenario. So both these components are experiencing the repeating process of charging and discharging when there is AC current flow. Overall, the mean power or the average power dissipation in either the inductor or the capacitor would be zero in a complete cycle of waveform. We also can link to what we have learned before when they are in DC circuit. When the energy is increasing in the inductor, it happens when there is increase in the current flow. We have learned that there is back EMF induced in the inductor, so there is work done to overcome the back EMF, which is converted to the energy that's stored in the inductor. And this is the opposite way when the current is decreasing, that the inductor will supply the energy back to prevent the decay in the current. And as for the capacitor, we have learned that the capacitor is charging when we turn on the switch in the DC circuit. And the scenario is quite similar in an AC voltage, that when the voltage increases, the capacitor is charging and vice versa. So we can see the similarity between the inductor and the capacitor. So this is how I do my revision on the inductor and the capacitor. So that's all for my video today. I hope you won't be confused by the two topics combined in this video. If you have any question, you can leave it in the comment section below. Also, do leave a like and subscribe my channel. I'll see you in my next video. Thank you.